Good day and welcome back. This is part two of our video series dealing with an introduction to three-dimensional space, essentially laying some of the groundwork for what's to come this semester. Now, in the previous video, we finished up by sketching a surface. And remember, a surface is an indication to us of the fact that we'll be dealing with three-dimensional space. And if we were in class and we were covering this material, this is the time where I would ask you all to turn your desks, work with your neighbors for a few minutes, and maybe spend 4 or 5 minutes and see if you can come up with a graph of this surface, x equals y, and particularly just the part in the first octant. So what I'd recommend doing is pause your video for a few minutes and see if you can come up with a sketch. Okay, so I've paused my video for a few minutes, and hopefully you have as well. If not, hit pause and really do this. And similar to how we started off our example previously, I'm going to think of this as a set. We are looking for all points of the form xyz such that x is equal to y. And remember, the key observation is instead of thinking where the restrictions are, is to think about where the restrictions are not. Here, z can be anything. So if we would like to sketch the surface, we will think about maybe the easiest possible value of z that we could choose. So let's go ahead and just add another note here. If z is equal to 0, that puts us in a very familiar setting. That puts us simply in the xy plane, which is ideal in a sense because the xy plane is what we are most familiar with. In our first octant we've sketched above, if I want to try to give it a little bit of depth, you have the xy plane, is determined here by the x-axis and the y-axis, and it really extends indefinitely. But in that xy plane, if we wanted to sketch x equals y, it would be this familiar line that we've drawn many times in our experience. But note, if we really want to get this surface, we have to take into account this idea that z can be anything. This first line we've drawn is simply corresponding to what happens when z is 0. But if z can be anything, how I like to visualize this is just taking this line and dragging it up in the z direction. And what that will end up giving us is a plane and I'll put these arrows here indicating that it goes on indefinitely. And how I'm envisioning this is maybe we have a book and we've opened up the book so that we have the front cover and the back cover at this kind of perfect 90-degree angle. And then we have one page kind of coming out of it. And that page coming out of the book would be representing, in this case, the plane determined by x equals y. So just to give the reminder again, remember your pictures do not need to be perfect. Far from it. They just need to get that kind of key information across. I'd say with kind of the supporting explanation in this work, we would be good to go. So to finish up this discussion on three-dimensional space, I want to go to some familiar formula and objects. So if we want to do something like maybe introduce the equation of a sphere, we might need to know how to measure distance. But the really nice observation we're going to make is you just do exactly what is done in 2 dimensions, and then you add one piece to it to account for the third dimension. So for example, the distance between 2 points, P1 and P2, the notation that we would typically use is the absolute value of P1, P2. And if we think of our standard distance formula, if we just had the x and the y coordinates present, so pretend the z1 and the z2 are not there. The distance between those 2 points would be given as the difference between the x values squared plus the distance between the y values squared, and then we would take the square root of that quantity. Because we have a third dimension to worry about, we simply just add in this extra term corresponding to the third dimension. Similarly, if we wanted to find the equation of a sphere, whose radiuses are centered at some point, we can just extend what we've seen in the past for circles. If it was a circle centered at h comma k, we would say, well, x minus h squared plus y minus k squared equals the radius squared. But we have to add in that extra piece to deal with the third dimension. So z minus l squared. And let's go ahead and investigate a very common example. The most common example of a sphere that we will see is one of the form given here. X squared plus y squared plus z squared equals r squared. And just to see why this is so familiar and such a common example, recall from your previous experience. If we were to just cut out the z squared term, x squared plus y squared equals r squared is the very familiar equation representing a circle centered at the origin with radius r. So with that in mind, if we were to include now the z squared, what we have is the equation of a sphere with a center at the origin. So the origin in three-dimensional space would be 0, 0, 0, and radius r. And if we wanted to think about this graphically, so we have three-dimensional space, and we have a sphere centered at the origin. So roughly speaking, it looks something like this. And something that we will do frequently is at least label the positive intercepts. That is, where does the surface intersect with the positive x or y or z axes? So in terms of the y-axis, if it's radius r, we would have this point 0, r0. With the x-axis, we would have this point r0, 0. And with the positive z-axis, we would have 0, 0, r. And now I'd like to finish our discussion on three-dimensional space with an example that involves a little bit of algebra, since we haven't done any of that yet. So another typical question we may have encountered in the past would be we're giving some equation of this form and we're asked to maybe verify that it's a circle or an ellipse when we're dealing in two-dimensional space. And of course, our three-dimensional analog of that would be to show that this equation is the equation of a sphere. And recall what we would need to do. In order to see that this is really the equation of a sphere, we need to get it into this form that we saw on the previous page. So if we could somehow write it in this way, we could immediately say this is the equation of a sphere with radius r centered at the point h comma k comma l. So the first thing I'm going to do is just group together the corresponding terms. So on the left, we have an x squared and a minus 6x. We have a y squared and a plus 4y. We have a z squared and a 2z. And this is all equal to 11. And I realize 2's and z's look an awful lot alike, so I almost always put a little line through my z to distinguish the two. And now is just where we make the observation. If we want to write this as some quantity squared, x plus or minus something squared, I want you to think for a moment what mathematical tool is required to do that. And if you thought complete the square, I agree with you 100%. And my technique for completing the square is to really just think about it intuitively. If x squared minus 6x is going to be the first two terms of x plus or minus something squared, what would need to go with this x? And the answer is it would have to be an x minus 3. And note, if you do want a formula, how did we come up with that minus 3? We just took this number minus 6 and we divided it by 2. So this 3 is really just minus 6 over 2. And note, those are not actually equal to each other. If you were to expand out x minus 3 squared, it would be x squared minus 6x plus 9. So to make those equal, I need a plus 9. But since I'm dealing with an equality, I don't get to simply place a plus 9 here for free. We have to balance it. So a plus 9 needs to be placed on the other side as well. And we keep playing this game. In terms of the y coordinates, we have y squared plus 4y. So that 4 indicates that it should be a y plus 2 squared. But in order for that to really be a y plus 2 squared, we need to put a plus 4. A plus 4 on the left requires a plus 4 on the right. And in terms of z coordinates, z squared minus 2z would be the first two terms of z minus 1 squared. But in order for those to truly be equal, we need a plus 1. And now if we add up all of those numbers on the right, we have 25. And so we have truly put this in the desired form that we indicated at the start of the example. So to conclude, what we need to do is just describe this sphere. So note this represents a sphere with a certain center and a certain radius. And the radius is probably easier to see. The radius comes from 25 being r squared. So the radius is a positive quantity. In this case, it'll be 5. And it is centered at some point. And what I would like you to do is to take just a moment, pause the video, and write down what the center is for this sphere. Okay, now that you've done this, the center going from left to right here, paying particular attention to the form x minus h, y minus k, z minus l. The center will be 3 minus 2, 1. And note it's really this minus 2 that we have to be the most careful of. That y plus 2 is really y minus a minus 2. And this completes our discussion of three-dimensional space. And let me just remind you, if you have questions, do not hesitate to reach out to me via email or joining me for one of my virtual office hours. I also highly recommend going through the book, working many of the suggested problems. Our next topic will be on an introduction to vectors in the specific context that we will use them in our course. So stay tuned and take care.